We're discussing behavior of gases today. Your objectives are to be able to describe how pressure and volume affect each other and how temperature affects volume of gases.
Not loading.
We're putting the final pieces of the puzzle together on something we've been studying for a long time, and I'm going to give you the name for it now, which is kinetic molecular theory. We've been studying kinetic molecular theory, we just haven't been calling it that. You're going to see the points of kinetic molecular theory, and you're going to see how we've been discussing them. Question?
Why couldn't we just call it the kinetic theory before?
Why didn't we call it that before?
Yeah.
It just didn't seem relevant up until this point.
Okay.
We haven't put all the pieces together into one big group.
So
Now
is
we
it like
can.
a big puzzle?
Kind of.
Oh, good.
So, the basic parts of kinetic molecular theory are that all matter is made up of small particles. So we've learned about these particles. That these particles are in constant random motion. So the particles are always moving, and their movement is random. The first two we have spent some time on before. These other ones are a little newer, okay, which is that particles collide with other particles, with other objects, and if they are a liquid or a gas, they collide with the walls of their container. So as we learned about the states of matter, and we talked about how their particles move, that's where this came from. So it's relatively recent. Okay. And then the last piece is actually reaching back to our study on Newton's laws of motion, which is that we learned when objects, which includes particles, collide, they don't lose energy. That energy is passed from one particle to another. It might change forms, but it's not lost. It doesn't just disappear. When you put all these pieces together, you get what we call kinetic molecular theory, which is just a theory that describes how particles in matter behave. The last 2 points of this theory are important in explaining why gases are going to behave differently than solids and liquids. Because if we understand that the particles of gases are so far apart from each other and moving so much faster, we can understand why they might behave slightly differently than particles in liquids and solids, which tend to be much closer together. Changes in temperature and pressure and volume affect all substances, but they're much more visible and they have a much greater effect in gases than they do in solids and liquids. And that has to do with the nature of how fast the particles are moving and how far apart they are from each other. Okay? I can put a lot of pressure on a solid, but because its particles are already so close together, I'm probably not going to compress them much closer. Okay? I can heat up a solid or a liquid, but the particles can only expand so much before it changes state. So we see a lot greater variability in the particles of a gas, which is why temperature, pressure, and volume can affect them so much more than others. Pressure, which we're going to talk a little bit about now, is the amount of force applied per unit of area. You may hear people talk about pressure in terms of air pressure, which would be the pressure that the air in our atmosphere pushes down on the objects on Earth with. Pressure can also just be as simple as me pushing down on a desk, or you pushing the plunger in a, I don't know, one of those guns that pushes the caulking out. Like, that's pressure. Okay? Water pressure, yes. The force with which the water pushes on you when it comes out of a faucet is water pressure. When you take particles of gases that are moving around all the time, those particles in their constant random motion are going to collide with their container. And as a result, anytime they are colliding with their container, they're exerting pressure on it. If I take those same particles and I compress them down into a smaller volume, you're going to see some things happen. So just imagine I have like a cylinder of gas and it has particles in it. And then I take a plunger and I push down on the gases and condense them into a smaller area. Okay? That's what we're talking about. They have less volume to move around in. What's going to happen is they have less room to move. As a result, they're going to collide with their container more frequently. And that increase in collisions is going to translate to more pressure being applied to the container that they are in. You observed this in your lab yesterday when you had the balloon stretched over the plastic bottle. If you squeezed the plastic bottle, what you did is you made the plastic bottle have less volume than it did before. So you compressed all of that air that's inside into a smaller volume. And as a result, the pressure on that air that air exerts on its container went up. And because a portion of your container, the balloon, is flexible, that increase in pressure translated to the balloon inflating. The opposite of this is true if you increase the volume. So when you released the plastic bottle and the volume inside increased, the particles had more room to move around, which means they collided with their container less often, which means there was less pressure exerted on the container, and as a result, the balloon deflated. This only holds true, this connection between pressure and volume, if you keep the temperature of the gas constant. This is a principle studied by a scientist whose last name was Boyle, and therefore we call this principle Boyle's law. When we write Boyle's law out, we write it as the pressure of a gas increases if the volume decreases, and the pressure of a gas decreases if the volume increases when temperature is constant.
Wait, do I have to write this?
You can restate Boyle's law mathematically using an equation that relates pressure and volume before a change to pressure and volume after a change. Looks like this. They're saying volume 2 is equal to pressure 1 times volume 1 divided by pressure 2. When they say pressure 1 or volume 1, they mean the pressure and the volume before a change happens, and pressure 2 and volume 2 are the pressure and volume after a change happens. You're going to get a chance to practice this in a practice problem. We measure pressure in kilopascals, so that's what that abbreviation means. And as you know already, we measure volume often in milliliters. So what I want to know is, what is the final volume of a gas that has an initial volume of 50 milliliters if the pressure increases from 600 kilopascals to 900 kilopascals? Remember that you're using the equation from above, so that's volume 2 is equal to pressure 1 times volume 1 divided by pressure 2. So you have to identify what's pressure 1, volume 1, pressure 2, so you can solve. I'm going to draw this a little bit better.
Well, I don't know.
Charlie, Snapchat.
So if we're looking at the problem, they give you an initial volume, which is right here. That would be volume 1. And they give you the starting pressure, which would be pressure 1. And they give you the final pressure, which would be pressure 2. So then all you have to do is plug those numbers in to solve for the final volume, which is volume 2. So if you take your initial pressure of 600 kilopascals times your initial volume of 50 milliliters and divide it by 900 kilopascals, you will in fact come up with a volume of 33.3 milliliters. We're going to round to 3 decimal places. Okay? Make sure you have a unit on it. In science, we always include a unit, and the unit here is milliliters, because you'll notice that the units of kilopascals cancel out. All right. Temperature also affects the behavior of a gas. When you increase temperature, what you are increasing is the average kinetic energy of the particles. Temperature is a measure of average kinetic energy. So when it goes up, you know that the kinetic energy of the particles is increasing. This means that the particles are going to move faster. More kinetic energy means faster moving particles. The faster those particles move, the more often they will collide with each other and with their container. The more they collide, the higher the pressure from the gases will be, and therefore, the higher volume that object will have. So, as you increase temperature, you should see an increase in volume. You saw this yesterday in the lab that we did when you put the flask with the balloon on it on the hot plate and it heated up. The particles inside gained kinetic energy, moved faster, collided more, and increased the pressure inside the balloon, causing it to inflate. But the opposite is also true. When you took that flask off of the heat and put it on the desk, and then later into the ice water, you were decreasing the temperature, which caused a loss of kinetic energy, slower moving particles, fewer collisions, lower pressure, and the balloon deflated. What we've just described is called Charles' law. Charles' law is stated as the volume of a gas increases with increasing temperature if the pressure is held constant. So, because both pressure and temperature can affect volume, you have to hold one of them constant in order to see the trends in the other one. All right. That should be the end of your notes for today.